Today, synthetic sapphire is playing a larger and growing role in our day-to-day lives. Synthetic sapphire wafers are used in the manufacture of cost-effective, energy-efficient LED lights. LEDs, the lighting of the future, offer high energy savings and are rapidly replacing incandescent and fluorescent lighting around the world. Semiconductors in electronic devices, phosphor plasma televisions and scratch-proof watch faces are some of the many applications that belong to the sapphire family. Smartphone manufacturers are already making the exciting transition to the unscratchable synthetic sapphire display screens. Lithium-ion batteries, where high-purity alumina is used in the battery separators, are underpinning the global transition to safe electric vehicles and renewable energy storage. To meet this rapidly emerging sapphire and high-purity alumina future, Altech Chemicals, an Australian company, is aiming to be the world's leading supplier of high-purity alumina. Altech Chemicals is now poised to become a world-leading producer of the critical ingredient for the manufacture of synthetic sapphire and lithium-ion batteries. High-quality, high-purity alumina. Altech Chemicals, meeting a sapphire and high-purity alumina future.
Please welcome Iggy Tan.
Good morning, everyone. Our vision is to build a 4,500 tonne per annum high purity alumina plant. And the product that we intend to make is a purity of 99.99%. So it only allows about 100 parts per million of impurities. And they use high purity alumina to make synthetic sapphire today. So sapphire in the Earth's crust is actually formed from alumina, a bit like carbon forms diamonds. And the reason the sapphires are blue color is because of impurities like iron and chromium that creates that blue color. Today, if you want to make synthetic sapphire for your watch face and your camera lens, it needs to be crystal clear. So you need to start with high purity alumina. How does that compare to smelter grade alumina that Alcoa produces? Well, that's about 99.5% purity. It looks pretty pure, but you can't use it to make synthetic sapphire because sodium, there's lots of sodium impurities because they use sodium hydroxide as part of the Bayer process. It gets locked into the crystal structure. It's very difficult to remove. Typical of these materials, the price is exponential as you go up in purity. So smelter grade aluminum might be worth 400, 3 nines might be worth $9,000 a ton. You get to 4 nines, it could be up to $35,000 to $40,000 a ton. So exponential growth. The two industries that are driving the growth of high purity alumina is in the LED industry as well as the lithium battery industry. So every LED is actually a semiconductor, light emitting diode. And to make a semiconductor, you need a wafer substrate. So in your laptops, you use silicon wafer substrates, but for LEDs, you need sapphire wafer substrates. Now, the way they make it is they buy high purity alumina, they heat it up in a furnace at 2,000 degrees, it melts and then it cools over 21 days and it grows a single crystal of sapphire. It looks like a big ice block, but it's very hard. It's a hardness index of 9. From there, they core it out using diamond cores, slice it up into wafers, and that is the building blocks of the LED industry. They put chemicals on it, electronics on it, you apply electricity and it produces light photons. And as you know, LEDs are very efficient in energy. It uses 1/6 the amount of electricity. The other industry that's driving the growth is in the lithium battery industry. You heard of the Samsung Galaxy battery fire. When a battery catches a light, is you have a thermal runaway. And that's when the positive and negative terminal touch and you get that thermal runaway. So in lithium batteries, there is actually a plastic separator that keeps them from touching, and it allows the lithium ions to go back and forth. Now, these separators are made of polypropylene, and they tend to shrink because the energy density of these batteries are getting hotter and hotter, and the temperatures are getting hotter and hotter. So But if you incorporate high purity alumina in these separators, it maintains the integrity. Now, previous speakers have talked about the cost of batteries coming down, so these are the blue bars. And the reason the cost is coming down because the energy density is going up. You're packing a lot more energy in a fixed volume. Now, how do you achieve that? Toby talked about the cathode material changing to more nickel and cobalt. So you see here, as you go to the right, more nickel and cobalt is driving the energy density. The consequence of that is these batteries are operating at a higher and higher temperature. You only have to leave your iPhone on and you can feel the heat of that. Imagine that in an electric vehicle. So lots of temperature in batteries today. This is a typical separator, handles about 100 degrees. If you incorporate high purity alumina in these separators, they can handle up to 300 degrees. So the consequence of that is that today, separator companies like WScope 2 years ago were only coating their 12% of their separators were coating. Today, up to 50% of their separators are coated. So you see this massive penetration. Now, what's the forecast for high purity alumina in that context? Now, CRU did a forecast. Currently, 30,000 tons per annum are used around the world. It's expected to climb to 270,000 tons per annum by 2028. 68% of that will be from the battery industry, and then the balance from the LED industry. Now, CRU also did a supply and demand forecast, assuming that all the projects that have been announced come on stream, you're still going to have 20,000 tons per annum deficit by 2021 and 50,000 tons deficit by 2028. Now, 20,000 tons per annum is 4 times our plan. Even after we build our plan, there will be a deficit of 4 times. So how hard is this sapphire material, which is usually on your watch? This is the watch face of the Apple Watch. And we got the Australian cricket team to do the scratch test here. So there are no scratches on that watch face because that actually has a hardness index of 9 and the drill bit is probably about 7 or 8. So you can go home and try that, put a drill through your watch, and if you actually start bleeding, then you don't have sapphire on your watch, right? Okay, let's look at the current producers of high purity alumina. They are chemical companies like Japanese companies like Sumitomo, Nippon Light. They're French companies, South African groups. So what you notice about the current producers is fragmented. It's not controlled by the Chinese like the rare earths industry. Now, how do they make high purity alumina? This is really the key. Remember I said there was too much sodium in that smelter grade alumina? They have to use aluminium metal as their feedstock. So they buy aluminium metal, they dissolve it in alcohol, they hydrolyze it and calcine that back to alumina. Now, where does aluminium metal come from? It comes from the bauxite process. They make smelter grade alumina. They sell it to the aluminium refineries. They add a lot of electricity and costs, and then they go back to alumina. It doesn't make sense, does it? Because it started from an alumina. So my question to you is that if you have technology that can actually bypass that aluminium metal stage, go straight from the ore to the alumina in one single step, are you going to be disruptive and are you going to be the cheapest cost producer? Well, at Altech, we have that technology. We go from the ore to the alumina in one single step, but we don't start with bauxite. We start with kaolin. Now, kaolin, as you know, is a highly weathered material. A lot of the impurities have been leached out. So look at the iron content of kaolin versus bauxite. Only 0.4% iron, bauxite's something like 20%. But lots of alumina and lots of silica, which we filter out in the process. The deposit is in Meckering, Western Australia. We've got nearly 250 years of material. It's ready to go. We have mining and works approval done. And kaolin is such a soft material. We can actually just free dig this material. We actually only need 50,000 tons a year. So we campaign mine this. For 2 months, we can dig 3 years worth of material. We then stop mining and then we go into a loading operation. The plant that we intend to build is in Johor in Singapore. Right across the road, there is a industrial park there. And in that industrial park, we have hydrochloric acid, natural gas, electricity, and a very sophisticated sea container port close by. The best thing about, we looked at all countries around the world. Today, if you want to compete globally, you have to be one of the lowest cost producers. And we like Malaysia because of the essentially the cost. So if I had to do this in Australia, my acid would cost $350. In Malaysia, it's $120. My electricity would cost 26 cents a kilowatt. In Malaysia, it's 12 cents a kilowatt. And the best part is that we also have a 5 to 10 year tax-free window. My comment there about no radioactive waste, you know why that is. So we don't have the issues of Linus and so on. The project itself, the chemistry is very simple. The first part is to remove the sand from the kaolin. The second part is to activate the kaolin. The third part is to dissolve it in hydrochloric acid. Fourth part is to purify the material. And the fifth part is to convert it to the oxide. So very simple chemistry, right? Everyone understands that? If you actually Google kaolin to alumina using hydrochloric acid, you will find that the Swiss came up with it in the early 1900s. The chemistry of it has been around. Alcoa and the US government did a lot of work in the 80s, but there was no demand for high purity alumina in the 80s. There was no LEDs, there were no lithium batteries. So because of the demand today, companies like us applied the same chemistry to our deposit in Western Australia. Works really well, makes high purity alumina at nearly the third of the cost. And you can see here the cost profile. We're nearly a half to a third because we don't use aluminium metal. We own the alumina in the ground for free. We recycle all the acid that we use in the process, and we're in a low-cost country like Malaysia. Now, what about the offtake? We have a 10-year offtake deal with Mitsubishi. They will buy our product and sell it to their customers in the LED and the lithium battery industry. What's great about this contract is that we get paid directly as soon as the product leaves our gate, and we haven't fixed the price. Because if you look at the demand and supply, you look at Toby's price curve going forward, it is at the market price with a 5% margin that Mitsubishi takes. All right. What are the risks of building the plants? I read a recent article that 79% of projects have cost blowouts, delays, and don't meet capacity. So we've teamed up with a German company called SMS Group, and we've got them to give us a fixed price lump sum contract. We've got them to give us a throughput and quality guarantee. Very unusual contract. Now, this is a very big group. They turn over about 3 billion euros a year. They've got about 1 billion euros in the bank, so we're not dealing with a small company here. This is a very quick look at the design of the plant, all pure German engineering. This is the area where the sea containers get tipped over into the process. Now, 50% of the equipment is German equipment, very sophisticated because you're actually targeting very high purity materials. And the capital cost is about 298 million. And as I mentioned, SMS will give us all the contract guarantees and so on. Economics. The NPV for the project is about $500 million US dollars. It generates around 76 million EBITDA or net cash at its full rate. The cost of production is about $8.55 a kilo. We, in our banking model, use $26.90 a kilo. And if you see Toby's graph, it's actually a lot of upside. So if you plug in $40 a kilo, that NPV goes to 1.2 billion. The company itself, 5 years ago, we're a $5 million market cap. We hit 100 million. We focus on building the project. We don't generally look at the share price. It will fluctuate. We focus on building the project. We have great shareholders. Malawa Group is a #1 shareholder. Deutsche Balaton out of Germany, and also SMS Group. All right, funding. Out of the 300 million capex, we have another 100 million of financing costs, which includes contingency, debt service coverage, working capital, and so on. So out of that, roughly 400 million US, 190 million of senior debt is now completed. This is funded by a German bank called KfW IPEX Bank, of which 170 million is export credit finance. Well, what's export credit finance? It's that the German government underwrites the project because there's so much German content. The EPC contractor is also a German company. And guess what my loan is? What's the coupon rate on my loan? It's LIBOR plus 2.5% for 14 years. All right, so pretty good loan, probably the best in the world, but you can imagine how much due diligence we had to do to get there. So 18 months of DD to get to that. Because the project is so cash rich, we can slot in more debt. So we've got a mezzanine debt piece from Macquarie Bank. This is going through its due diligence. So we are in the final stages. We've done the technical DD, the market DD, and then we are moving on to that. So rather than wait for financing to all finish, well, what we decided is, why don't we start building the project? So we funded, in the last couple of years, we raised about 40 million of equity, and essentially we've started building the project. That way you take the risk of permitting. It's demonstrating that we're getting on with the project. Who thinks that's risky? I actually asked that question to a couple of German banks, and they said, no, actually, you need to get going with it. So the strategy is to run the construction process at the same time as we finish the debt process. Okay, very quickly as I wrap up with the German strategy, this is really a fast-moving area you want to look at. Europe is really pushing with EVs and the battery space. They really driven by the 2020 EU CO2 emissions, so all automakers have to be less than 95 grams per kilometre. A diesel car is about 130 grams. A petrol car is probably about 160. So to get to the 95, half their fleet has to be EVs. And this is the big movers. When the German automaker starts to get into EVs, you're going to get serious, right? This is the Taycan. I'm sure Liam's got one of those, a sports car. It goes for about 450 kilometers before you have to recharge, 0 to 100 in 2.8 seconds, something like fantastic. When the European auto industry gets serious about EVs, watch the space. We are focused on building the first plant. But if you look at the supply and demand, we need to start planning for the second plant. We have been invited from the East Germany to build the second plant there, to consider building the second plant, and we're currently looking at that. Okay, just wrapping it up, we need to raise roughly 100 million US. There are two options. First, find a joint venture partner, which is what we're doing. We sell 49% for 100 million, we've got a joint venture partner. The second strategy is we acquire a separate German listed company, which we now rename Altech Advanced Materials, and we sell them the option to acquire 49% of the project, as long as it raises 100 million. Now, why is that strategy important? Because a lot of investors in Europe understand the implications of KfW buying SMS, etc. A lot of Asia don't understand the significance of that bank. So it allows the European investor to invest in the project. And so this is the structure very quickly. 100 million gets raised in this separate company. It then owns 49%, and we're joint venture partners. The best part is that we are actually also on the board of this company, and we generally run the company. But we also offer a buyback. So after year 6, we buy the project back at 49% for a 15% compound rate. So it guarantees that return for that German company. Why? It's because we want to own 100% in the long term. All right. I will close and say thank you very much for your time. And if you're looking for the next lithium boom, it's probably going to be high purity alumina. Thank you.
Brilliant. Thanks, Iggy.